Hi everyone, I am Sim Hui from Group 5. My group members and I are going to talk about Chapter 4.3 Specific Latent Heat. In this subtopic, you will learn latent heat, specific latent heat of fusion and vaporization, heating and cooling curve, and the last one, application of specific latent heat in daily life.
We can see some example of latent heat. Latent heat absorbed when ice changes to water at melting points. Latent heat also absorbed when water changes to steam at boiling point. Latent heat released when steam changes to water and vaporization points, and also released when water changes to ice at freezing point. Next, we will see change of mass and latent heat. When a solid is heated, its temperature increases and the solid may turn to liquid. The process by which solid changes into liquid is known as fusion. The temperature at which the fusion is occurs known as the melting point. The temperature of liquid will continue to rise after all solids have melted. Continuous heating may cause the liquids to turn into gas. The process by which a liquid turns into a gas is called vaporization. The temperature at which vaporization occurs is called boiling point. Next, we will see specific latent heat. The quantity of heat needed to change the state of matter of an object depends on the mass of the object and its material. Specific latent heat L of a substance is the quantity of heat Q that is absorbed or released during a change of mass of 1 kg of the substance without any change in its temperature. An object of mass m absorbs a quantity of heat Q during a change of pressure. Therefore, specific latent heat of the substance of the object is L is equal to Q over m. SI unit of specific latent heat is joule per kilogram. Latent heat. When water is heated, the temperature of water begins to rise until it starts to boil. During boiling, the temperature of water remains at 100 Celsius, even if the water continues to rise. The temperature of the boiling water is equal to the temperature of the from steam, which is the absorbed heat used to convert the water to steam without changing the temperature. If steam is converted to water at 100 Celsius, heat is released. The conversion of heat to water, which is condensation of steam, also occurs without temperature change. The heat absorbed or released when a substance undergoes a change of pressure without a change in temperature is called latent heat.
Hi everyone. Now I would like to talk about specific latent heat of fusion. Specific latent heat of fusion is the amount of heat energy required to convert 1 kilogram of a substance from a solid phase to liquid phase without any change in temperature. We can use this symbol to represent the specific latent heat of fusion. Heat energy Q required to convert m kg of a substance from solid to liquid state at a constant temperature. We can use this formula to solve problem. Q is equal to ml, where Q represent heat energy, m is represent mass, and L is specific latent heat. The SI unit of specific latent heat of fusion is joule per kilogram or joule per gram. Next, let's look at this. Specific latent heat of fusion of ice is 3.34 times 10 power 5 joule kilogram negative 1. This means 3.34 times 10 power 5 joule of heat energy is required to convert 1 kilogram of ice at a constant temperature of 0 degrees Celsius to water and 3.34 times 10 power 5 joule of heat is released when 1 kilogram of water freezes to ice at 0 degrees Celsius. This diagram shows that the specific latent heat of fusion of ice converts to water. Now I will talk about specific latent heat of vaporization. Specific latent heat of vaporization is the amount of heat energy required to convert 1 kilogram of substance from a liquid phase to gaseous phase without a change in temperature. The symbol of latent heat of vaporization is LV. Heat energy Q that is absorbed during boiling, or the quantity of heat released during condensation of 1 kilogram of the substance without any change in temperature. We can use this formula to solve problem. Q is equal to mL, where Q is heat energy, m is mass, and L is latent heat of vaporization. The SI unit of vaporization is same with the specific latent heat of fusion. Next, let us look at the specific latent heat of vaporization of water. Specific latent heat of vaporization of water is 2.26 times 10 power 6 joule per kilogram. This means 2.26 times 10 power 6 joule of heat energy is required to convert 1 kilogram of water at constant temperature of 100 degrees Celsius to steam, and 2.26 times 10 power 6 joule of heat energy is released if 1 kilogram of thin condensed become water at 100 Celsius. This picture shows that the specific latent heat of vaporization of water is required to convert 1 kilogram of water at constant temperature.
I'm going to talk to you about heating and cooling curve. Let's look at heating curve first. In heating curve, the staircase is going up as the temperature is increasing. When the temperature is increasing, the heat is absorbed. The temperature increases means that heat is absorbed, and temperature increases. When heat is absorbed, the molecules gain more energy and the kinetic energy of molecule increases too. From PQ is a solid. When it comes to QR, the solid is undergo melting process, but it not yet become liquid. When we come to RS, the solid already become liquid. And during ST, it undergo boiling process. And finally come to TU, the liquid during boiling the liquid changes to gas. Before we move to QR, I want you to know that heating can refer to melting or boiling process. Now we look at QR. QR is a melting process which changes solid to liquid. At point Q, solid starts to melt. During QR, solid is melting, and at R, the whole solid has melted. Latent heat is absorbed to weaken the bond between molecules. There is bond between molecules. As we know that the molecules of solid is packed closely together. When we want to melt solid to become liquid, we must break the bond. When we break the bond, molecules are released from their fixed position and move throughout the liquid. And during melting, there is no change of temperature, and kinetic energy of molecules does not increase as there is no heat is absorbed. Now we look at RS. Liquid is increased. Liquid is heated until boiling point. Heat is absorbed, temperature increases, and kinetic energy of molecule increases. Same as the PQ. Now we look at ST. ST is a boiling process. We change liquid to gas. At point S, liquid starts to boil. During ST, liquid is boiling, and at T, the whole liquid has boiled. Later heat is absorbed to break the bond between molecules. Same as the melting process. We need to break the bond so that the liquid can become gas. When we break the bond, the molecules are separated far from one another. Kinetic energy of molecule does not increase as the heat is not absorbed, and the temperature remains constant. After boiling, we come to TU. At TU, gas is heated, heat is absorbed, temperature increases, and kinetic energy of molecules also increases. That's all for heating curve. Now we move to cooling curve. Just now, in the heating curve, the staircase is going upright. Now we are at the cooling curve. When we cool a substance, the temperature will decrease. So the staircase of cooling curve is going down. When we cool a substance, the temperature decreases. Temperature decreases means that heat is released. When the heat is released, the molecules lose energy, so the kinetic energy of molecule decreases. At PQ, it is gas. When we come to QR, the system undergoes condensation process and from gas become liquids at point R, and RS is liquid, and when we come to ST, it undergoes freezing process, and when come to TU, the liquid freeze into solid. Now we look at PQ. Gas cools to boiling point. Heat is released, temperature decreases, kinetic energy of molecule decreases. The same thing in heating curve can refer to melting and boiling, and in cooling curve it can refer to condensation and freezing process. Now look at QR. QR is a condensation process. It changes gas to liquid. At Q, gas starts to condense. During QR, gas is condensing. At R, the whole of the gas has condensed. Later heat is released and molecular bond is formed. During heating, when we want to melt a system or boil a system, we need to break the bond, right? Now in cooling curve, we want to make the gas to become solid. We want to make a molecule that far apart from one another to make it packed closely together. So we need to form a bond. When the bond is formed, molecules move throughout the liquid. The same thing, kinetic energy of molecules does not decrease because it is horizontal line. The condensation is undergoing. There is no change of temperature. Now look at RS. Liquid cools to freezing point. Heat is released, temperature decreases, kinetic energy of molecule also decreases. Now look at ST. ST is a freezing process. It means that we change liquid to solid. At S, liquid starts to freeze, and during ST, liquid is freezing, and at T, the whole liquid has frozen. The same thing, latent heat is released so that the bond between molecules is strengthened. When the bond forms, the bond between the molecule is strengthened. The molecule can vibrate around a fixed position. It means that the liquid already becomes solid. This is horizontal line, so there is no heat release, and kinetic energy of molecules does not decrease, and the temperature remains. After freezing, the liquid already becomes solid. At TU, solid cools, heat is released, temperature decreases, kinetic energy of molecule decreases. That's all for cooling curve.
Hi everyone, I'm Dr. Smasinho, and now I'd like to present the application of specific latent heat in daily life. This diagram shows that the cooling system in refrigerator. A refrigerator uses the cooling effect from evaporation. During circulation of the cooling agent, heat is absorbed from inside the refrigerator and released outside. This shows that compression compress cooling agent to increase pressure and its temperature. In the condensation, cooling agent release latent heat during condensation. Cooling agent flow through expansion valve. In the evaporator, cooling agent evaporated and absorb latent heat from inside the refrigerator. Cooling agent flow out from evaporator through the compression. Next, this shows the evaporation of sweat. We sweat on hot day or while doing heavy work. When sweat evaporated, heat is absorbed from the body, causing a cooling effect. The rate of evaporation increases when there is air circulation. That's all from our presentation. Thank you.